So I geared it towards the audience, and the ask was step by step. So I tried to combine the approach, the methodology, and try to get in a live example of when and how we will actually work through these steps. So I may not get to the entire thing during this 50 minutes presentation, but at least I'll leave you with a guide, sorts of. And then this is also in my book, chapter 5. So anytime you want to reach out and have any questions, please feel free. I will also send my email address and everything after this presentation, so everybody has my contact information. I'm Monica Beckwith. I'm a Java champion, and today I'm going to talk about performance engineering step-by-step in Java. This is basically a dynamic approach to Java performance optimization. What that means is that you can apply it to any application, and you can have, even if you don't have a full view of the stack. So you only know your Java application, or you only know the Java virtual machine, the JVM, the garbage collectors, but you can apply this approach to cater to your performance needs. I'm going to quickly talk about the agenda, and then basically what I want to do is set the stage for performance engineering. And what do I mean by a basic application stack? Okay, so we'll just quickly go through that. And then I'll talk about the methodologies that I was talking about. The two main things that many people in performance engineering discuss when they talk about methodologies is the top-down and the bottom-up approach. They're kind of just the way you want to tackle the domain, the performance domain for your application, for any application. But I want to talk about it in very specific needs of the Java application stack. The other approach you may have heard of is the experimental design, as in how do we approach a performance engineering problem? How do we, get a benchmark and then make sure the variables are aligned to what we want to measure, and identify different problem spaces that you want to attack or tackle to be able to get to your performance service level agreements for your application. Or if you're doing a garbage collector, for example, or if you're evaluating a garbage collector, then you want to try to help the garbage collector to achieve its SLAs as well. So it's both approaches, but experimental design kind of helps those two methodologies. Then we'll talk about benchmarking and, of course, these approaches, like how do we kind of combine and work towards what we want to achieve. And I will introduce a case study here. I'm going to use a very simple Spring Boot pet clinic application. What I want to do is I want to try this new generational garbage collector, which is the ZGC. So ZGC has been fully supported since JDK 15. And it was single generation. And just recently, efforts have been made by Eric Osterland to make it generational and also very much adaptive. I will not go into the details of the garbage collector. I'll just give you an overview because of the time constraints.
Please mute your microphone.
So just because this is more about performance engineering and methodology, so garbage collector could be another talk. I'll come next time and talk about that. And then finally, I'll do a key takeaway, as in what did we do and how did we bring it all together? And that would be the last slide of this talk. So let's dive in. So what we want to cover in this presentation is how to systematically approach performance engineering. And basically, we want to make sure that our Java application, in my example, it would be the pet clinic, it remains performant under various conditions. And the various conditions that I would have in my case study would be trying out a new garbage collector, which is the generational ZGC. right? But for your case, it could be various other things. You have changed a library, you have changed you have upgraded to a new JVM, or you have upgraded your own software and kind of changed the way allocations happen, right? So there's lots of things that can happen. We're trying to go and identify these problem spaces and then how to refine them and tune them. And that's where the methodology comes in. So the way I define performance engineering, and it is not just applicable to Java, it's applicable to the performance domain. And basically, performance is something that's very crucial to the success of your application. It directly impacts user satisfaction and the business outcomes, right? So another way to think about this is when you're looking at performance, you're thinking about how swiftly and seamlessly the application responds to user interaction. So it doesn't always mean that the user has to physically click on something and that's an interaction. The user interaction means a request, right? And it could be from a database, it could be from network. So that all constitutes as your interaction. And then how quickly you respond and how seamlessly the components integrate. So if you're going to call a Netty library, for example, how seamlessly are you getting the information, the HTTP over HTTP or whatever, and then how quickly you're processing it. So that all is your entire system and how we are interacting and kind of communicating with it. So what happens in modern software systems, you have high user expectations, so it's not about just being responsive, but also get the feedback. So it's a request, response, and an acknowledgement sort of, right? And that kind of keeps the engagement and satisfaction level high. So you could have requests coming in and the response going, but then the acknowledgement that we can go on to the next one, it kind of helps with the async nature of systems nowadays. So if, for example, if you have a mobile banking app, the application, if it lags while the transactions have been processing, the user may feel very frustrated, right? Maybe you're lagging because either in your database connections or you're just the read write sequence, the transactions that are happening, right? And then now users are losing trust in that service. But when you have a seamless experience, the user feels more confident and kind of wants to use the application even more, in an interactive space. So one of the things that we have to ask is this question. So now I've given the definition, but like why? Why does performance matter? We know the what of performance, but why does it matter? And it matters because performance is a key quality attribute. So it's not only highlights the efficiency of operations, but it also highlights the user experience. So basically, if you lose users, and that kind of directly affects cost of goods sold, COGS, which means the revenue. And then if you have lower revenue, then your operational costs become really high. So basically for your same application to maintain, to upgrade software, to maintain the developers' happiness and all those things, you need to have a steady operational cost. But losing revenue automatically equates to higher operational costs. And we're going to talk about efficiency of operation as we talk about the Spring Boot app. And user experience is kind of like, I'll just briefly mention it, but remember that it's all about the end users. When we're designing a statement of work, when we're talking about performance, it's about the service level agreements, the service level objectives, and these are something that your users are defining for your system and your application. So let's quickly look at the Java application stack. And I've kind of made it very simple because I want to talk about each of these spaces without spending too much time in it. And I want to basically cover some tools and everything that may be useful for your daily application analysis. So we have the stack that begins at the hardware level. So we'll go from the lowest layer, which is the hardware layer. And then it builds up through the operating system and the Java runtime environment and the virtual machine, which is the virtual machine is a component of the runtime environment. So depending on your hardware, so if you have an ARM64 hardware and say a Windows operating system, then your Java runtime environment will be geared towards the Windows and ARM environment. And your JVM will work in that. So basically, your garbage collector understands the hardware and the OS. The compiler threads know exactly how to operate it on Windows and how to optimize its concurrency on Windows. Same goes with the garbage collector threads and so on and so forth. Class loading, everything is able to understand the environment. And then finally, it goes to the application layer and the application ecosystem. So each of these layers, they play an important role in the performance of your Java application. So we need to make sure that we have the ability to systematically analyze each layer, because a bottleneck, a performance bottleneck, a scaling bottleneck can be anywhere in this layer, and it can affect the entire stack. So we need to be able to visualize these problems. So let's start with the application stack. What does that mean, right? So basically, we're looking at the application services. And if you have an app server, then that also becomes a part of your application ecosystem. Then if you have databases, like even in-memory caching, that becomes your application and its ecosystem. If you have any other services in the ecosystem, right? All those become an important part of your ecosystem of the application. So you're not only looking at the application in isolation, you're actually looking at the the functionality and the interaction around the application. So what that means is that we're looking at it like through a lens of identifying any bottlenecks, right? So, for example, a slow database query or an overloaded application server can lead to increased response times, and it can directly impact user experience. Remember, we were talking about user experience, even though I'm talking about some tangibility with latency and throughput, but it boils down to your SLAs and how your user experience is impacted. Okay. The next one is the JVM, and I briefly covered this earlier. So basically, we're talking about class loading, we're talking about JIT compilation, we're talking about GC, we're talking about any threads, right? And by threads, as in, because the Java application threads are known as mutators, and they kind of do the allocations. So when we are talking about GC, we're not only talking about GC threads, but also how, from on the OS, I talked about Windows, for example, how scheduling happens, and on ARM architecture versus x86 64-bit architecture, if there are any nuances with respect to how the actual processing cores or the multiple hardware threads work, that also affects your performance. So the JVM is an execution, and as an execution engine, as a runtime engine, is equipped to understand all these hardware and OS level nuances and able to optimize on it. But as a runtime a performance engineer, we need to know that these interactions are happening, because that's what it means. Every Java code that you're executing boils down to how it gets translated to the hardware level instruction. So, and hardware level interaction. So it's important to know. Most of the time, people talk about garbage collection as being something that directly affects the way your application SLAs are met, right? And sometimes it's true that if you're spending too much time in garbage collection, which is called the garbage collection overhead, then it can lead to degradation of application's performance. So we'll look at this from the garbage collection point of view when we go to the case study. But something to keep in mind, there could be other problems, especially in the startup domain. You're looking at different things. So kind of like the performance domain shifts to like JIT compilation, thread activities, as well as class loading and everything else. So depending on the domain of your application lifetime, you could be concentrating on different things. So here we're just gonna, today's case study will only focus on the GC side of things. As I mentioned about operating system, I talked about the scheduling. So that's the system and kernel stuff and the threads and everything. But there's also the things that I didn't mention, which is locking. When you have a multi-threaded, multi-core environment, locking plays a very important role. And if you're thinking about, if you have looked at the news of Project Loom, and the lightweight threads, that's kind of like in this problem domain space. So the way Java handles threads, lightly contended threads, or heavy contention of threads, Java handles it in its own way with respect to parking or spinning and all those things. So there's a lot of optimizations with respect to that domain. And now we're getting into the Project Loom, the virtual threads domain. And understanding locks and how we are actually using the OS, the mapping of 1:1, or having multiple virtual threads to one carrier thread. All those things are really important when we're looking at the performance domain. Again, it's outside the scope of what I want to cover today, but something to keep in mind when you're looking at these newer Java projects, okay? Of course, we talked about threads already. The reason I want to highlight these things is because when you're doing a system level analysis using VMstat, and I'll talk about the tools, we have to look at the system and kernel statistics. We look at lock contention, context switching, either voluntary or involuntary, and we look at the thread management. So because all these will affect your system performance and your application is running on a system. It could be in the cloud, it could be in the container, but it is always running on a system, right? On a hardware system. So very important to understand that. Blocking threads due to locks, like heavily contended locks, like say if you have an atomic counter or something, and if it doesn't scale that well, those are also important, especially when you're doing parallel processing. So high performance application locking becomes a de facto concern in the sense that, are we scaling correctly? Are we scaling to the potential of the system, right? So something to keep in mind, although we won't dive into that today, but keep in mind. Finally, the hardware, the biggest influencer of your performance, the actual thing that will help you meet your SLAs, the crux of the execution. What's important here? Something that when we talk about GC perspective, we're talking about memory allocations, we're talking about memory pressure, we're talking about GC churn. What does it boil down to? It boils down to how effectively we are utilizing the hardware memory bandwidth, memory traffic, memory consumption. Like, how are we doing that? Why is that important? Because everything needs processing unit, like central processing unit, and each hardware core needs to be effectively utilized, and not utilized just in terms of execution, but also utilized in terms of its cache efficiency. So you're bringing the hardware cache, similar to how you would have a database cache. Similar to that, hardware keeps track of these kind of memory, like cache lines, they're called basically. And these are the data that you're reading or writing to, and it becomes a sort, you don't want to always go to the DRAM. You want to keep something in the cache, and how efficiently we utilize this cache is very important. Any other architecture specific differences? Like I said, sometimes you have hardware threads, sometimes you have just the cores, and there's a lot of other nuances of each hardware. And as you say, lift and shift in the cloud, you may observe that moving from AMD to Intel to ARM, gives you little differences in performance, SLAs. So something to keep in mind for the future, but right now we'll move on and talk about also the IO stat. So when you're doing, say, NetE level, library dependencies, or JEDI level library dependencies, IO stats are important. But let's move on to the methodology. So why is methodology important? A methodology provides us with a roadmap to investigate these subsystems that I had talked about. So what it does is that it kind of does this kind of checks and balances. So you have this kind of roadmap. This is the way we're going to approach this. And then you're going to say, okay, I haven't looked at this subsystem yet. And maybe that's where the issue is. So as you move down subsystem or move up a subsystem, methodology helps guide you. So it's kind of, think of it as a page mark, right? So you've done this, then the next one, we're going to flip the page, and then we're at this page. And then you can come back and continue, as long as nothing has changed in the stack, you can come back and pick up that from. So you can divide it over a number of days, a number of people, but as long as you have a methodology, then you all can contribute towards performance engineering exercise. And that's what the title comes from. It's like a step-by-step, right? So everybody understands, okay, today this is what we're looking at, and this is what I found. Let's see how that applies to the next one. And so that's why it's kind of important. As I mentioned, it's a systematic approach. So the reason we want to make sure that we understand the systematic approach is trying to break down, or kind of like deconstruct. So a complex application stack with its application ecosystem all the way down to the hardware, you want to be able to deconstruct it. So you want to I've done this, I've identified an issue. So that brings us to the next slide. So I have identified an issue, then I want to analyze the issue, and then I want to optimize the issue. So a methodology will guide us through all these things by showing us what tools we have, by showing us where we are in the stack, and basically the identity, the analysis, and the optimization will go and touch all the layers of the stack. So we need to be able to maintain that kind of connection and kind of proceed with that in mind. So let's look at step one, which is to identify the problem. So I talk about applications, systems, subsystems, but usually in performance engineering domain, we talk of everything as system under test. So it doesn't matter if you're just looking at one layer, but once you have identified that this is the domain, this is the stack that I'm going to study, then the entire stack becomes your system under test. So even if it's one application and 1,000 libraries or 1,000 dependencies on that, then even that whole slice would be your system under test. So that doesn't change as long as your methodology follows the same system under test. Then you're able to carry and kind of like analyze it anywhere in the stack. So once you have a system, that's your system under test, and that's what we're going to monitor, analyze, and improve. Okay. So the identity section, the step, helps us look at everything, look at the statistics, especially given SLAs. We're talking about system level agreements. So look at those and then identify areas of improvement. So what does that mean? It means capturing logs, right? We all, because we're looking at the holistic stack, we have the system log, the application log, the IO log, any kind of system memory usage log, GC logs, any kind of web logs if you're looking at some kind of web use cases. And so that all constitutes the first step of identifying where you can get your information from, like what you need to monitor. Okay. So what does that mean? We want to look at either active, passive, offline, or all of the above, right? So active would mean create alerts. Passive could be network taps, which means that you're just kind of making sure, say, you're netting traffic, everything else is like in place and doing what it's supposed to do, or any kind of bottlenecks that are there. So you would have some information there. And then offline would be all these logs that I was talking about, right? Any like GC logs you could do. You can also put alerts in GC logs as well. But in general, like if everything is working okay, then you just go do offline background monitoring or whatever. So these are the ways that you can approach that. Identifying the problem domain, and then these are kind of, they carry through to your applications and your stack. They're not very, especially in the Java world, they're not very, what is at the Linux level or Windows level. This is just identification. And some of them may be very particular with respect to identification, where you need to have specific tools for Linux and Windows. But because we work in the Java runtime space, these kind of are basically, you can just have them, and you can lift and shift your application, and you'll still be able to employ these, because that's the beauty of Java runtime. Write once, run anywhere, right? So kind of should work for you. Step 2 is analysis, right? Here we want to profile for hotspots, right? And then we want to profile for deep dive too. So once you have identified the hotspots in your step 1, then you want to go deep dive. And what does that mean? It means that we have, say, you find out that hash map is the caching mechanism that you've used, concurrent hash map or whatever. And that is having, that is, when you profile it, you see that as a very hot method, or multiple methods in that, getters, setters, whatever. And then that becomes your hotspot. And then you want to go and deep dive into that analysis and trying to figure out why that's happening, right? And here you will need some tools. And those tools could be Visual VM, Java Flight Recorder. So basically, once you have the hotspots identified, then you want to analyze them. And basically, you're diving in deeper. So that's what I want to talk about here with respect to the deep dive. How do we go into analysis, and what tools we have with respect to analysis? So the tools that I already talked about, Java Flight Recorder. One of my favorites is Async Profiler for Java applications. I also use NetBeans Profiler sometimes when I'm looking at trying to understand if I have a smaller, allocation domain that I want to analyze. I will look at the NetBeans Profiler as well, and JConsole to get some information as it's running, and or to tap into certain information. So that's also important. On a bigger scale, you have Perf, right? The Perf is available on various platforms now. Then you have OProfile, it's kind of older profiling tool, dtrace for others that have been working on Mac for a while, and Solaris, if you had ever had the opportunity to work on Solaris, that was really useful. And then lots of tools on Linux and Windows that are very specific to the operating system, which is great, right? Having knowledge of the operating system, this is why it's so important to understand the operating system. So you find tools that help you understand how the OS works, right? And so try to combine those to be able to analyze stuff. So now that we have analyzed and kind of catering to the domain that I was talking about with respect to GC, what do we want to do? So step one, we looked at the analysis, we found that there were some issues, but have we chosen the right GC algorithm? Like in my case, if I want to tackle latency, and I will go into what I mean by tackle but basically in OpenJDK, in the JVM domain, we have a lot of options with respect to GC algorithms, right? So we want to make sure that we're using the right algorithm for our application domain. So if our application needs are kind of like latency sensitive, or is throughput a concern, any other architectural concerns? Because remember, I talked about different architectures, and they have different operating space, and the garbage collectors sometimes work differently based on the architecture. Maybe some operations may be more expensive on certain architectures than others. And what about CPU utilization? We're talking about cloud, we're talking about containers, we're talking about utilization, and especially CPUs and memory also is a big concern. So you want to talk about, that's kind of like the footprint of either the CPU or the memory, or just shared IO or whatever. So that footprint is also a major concern. So we look at these GC algorithms through that lens of where do we want to operate? Where does our application need to operate? From the GC perspective, we want to make sure that we are using the right heap size. So age-old question is, should the XMX be the same as XMS? So XMS is the initial heap size, and then XMX is the maximum heap size. Should we keep the initial same as the maximum, or let the newer adaptive GCs adapt their nursery, adapt the nursery and their heap, and kind of go where they need to be? Okay. So so that's that. The next one is the heap sizing itself. You have to think about your footprint of your objects. So not only your long-lived objects, that are basically all the data that's needed for your application domain to work, but also any kind of transients, like as users have transactional interaction with your application, that transactions can have either transient space, or they're actually read and write updates to your database, right? So transactions can be any of those. So we want to make sure that we're accommodating for not only the live data, but also the transients, okay? The other thing, again, when we're thinking about containers and cloud, will you be a good neighbor? I'm pretty sure many of you have worked in this domain where you have a noisy neighbor. What does that mean? So basically, if you think about all these applications are working on the hardware and the operating system space. So as you go into cloud, you have the hypervisor and the guest OSs, but the underlying hardware, where you're working on, is the same. So the resources of the hardware, this is where we go back to the footprint concern, right? The resources of the hardware are still the same. So if you have a 128 core hardware, and your application domain, your container, your VM is only needing, say, 8 cores or 64 cores out of that total 128 cores, then the hypervisor and basically the cloud providers could pack another node on the same stack, right? So although because of security and everything, there is proper isolation and everything, but underlying hardware is the same. So when one neighbor is demanding some more resources than the other neighbor, then one of them is not being good, especially if you have only limited IO channels or things like that. So these kind of things, these noisy neighbor issues, we have to be aware for, especially in the container space. So that's one of the things that you can, and that can, a noisy neighbor, it may not just be you, it could be somebody else, but it can affect your SLAs. And then that's why the repeatability and reproducibility matters a lot, because sometimes you're with a noisy neighbor and sometimes you are the noisy neighbor. So we got to be careful about that. I talked about object lifetimes, you could have live datas and transients, but what is more important is when you're looking at, especially in our case study, we're looking at generational ZGC. So when you're looking at generational space, the whole premise of a generational collector is to age objects appropriately so that we can adhere to the hypothesis that most objects die young, right? So we want to age them, if they're long enough to live in the old generation, then we promote them. If they're not long enough, then we kind of let them die in the young space, right? So promote long-lived objects to reduce GC pressure. So because old generation also has its own collector, so you want to reduce the GC pressure. So that's the thing with the garbage collection side of things. What about GC worker threads? We won't be able to cover this today, but something to keep in mind is that as we are going towards these more adaptive garbage collection techniques, we are entering the domain of dynamic GC threads. So basically, your garbage collector is now choosing how to use your GC threads and how to kind of optimize it. But it's a good thing to, if you want to go optimize the GC work itself, it's a good thing to go and check for parallel GC threads and concurrent GC threads, especially G1 and ZGC both have this parallel and concurrent worker threads. So go look at those and check out the GC overhead. When I get to the case study, and I'll show you logs and where to look for how many threads were used, okay, and how the overhead is. Memory footprint optimizations. When you're looking at what footprint optimization means for your system, go ahead and use this tool called Native Memory Tracker. And what that helps is understanding like how we are doing with respect to the JVM's native footprint, right? So it's really important. And the last point I wanted to talk about was NUMA architectures. So not basically, this is again boiling down to the hardware where your non-uniform memory access patterns can have an effect on how your application behaves. So it sometimes may be important that you don't want your application threads to be scheduled out or context switched. So pin them. Sometimes it's very important, especially you're working on a stack that is doing a lot of heterogeneous works. So you want to pin down the application threads and make sure they always get those processors so that the first touch principle, where wherever you're allocating, the physical system is located, and kind of you're minimizing cross node traffic. So let's now dive into top-down methodology very quickly, because I'm very conscious of the time. It's the same application stack, but you see how kind of like the weight is different. Basically, what top-down methodology tells us is that we are aware of the holistic stack. We know and we understand the high-level objectives of the system, and then we work downwards. So from our application perspective, we're kind of looking into the platform, and that's how we work. That's the domain space that we know. So we know our application. Those are our known knowns. And there are some unknowns. We don't know how it operates on this platform. It could be a different garbage collector. It could be we just did a lift and shift into a different hardware architecture, or we're moving and testing on Windows versus Linux, right? So the platform may have incremental changes that we are not aware of, or we want to understand better. So that's when we apply the top-down methodology. One of the things that really helps us with the top-down methodology is to have a statement of work. What the statement of work is kind of like a compass, telling us what we want to do with that top-down methodology. And usually your statement of work is able to define objectives. Basically, we want to understand what we want to achieve with our problem, with a performance problem, and how do we want to solve it. Identify stakeholders. Basically, by stakeholders, it could be the operational teams, the developers, user experience for the developers themselves, or user experience for your business stakeholders. And any kind of performance goals, you want to understand that. And those, the stakeholders, the user experience teams will be the ones that will align your business goals. And then you will set performance metrics. You will plan and allocate and identify benchmarks, right? And basically what that means is that your application domain, and that, oh, I want to be able to benchmark these particular subsections first, and then kind of do a holistic, full system benchmarking. So that would be something that you would do with respect to like concurrent user load, or you want to do how effectively you're doing data processing and handling large volumes of data. And the second last, or almost the last one, is milestones. So you've identified all these things, then create milestones like initial baseline, first round of optimization, final performance evaluations. Those are all your milestones that you would have. And while we're doing that, we want to make sure that we want to identify risks and mitigation strategies, because you are aware of your application. That's the whole premise of a top-down methodology. We know our application. So we want to identify things like database latency, network limitations, and these kind of are becoming like, oh, we want to make sure that these are not turning into risks. And if they are, then this is how we can mitigate those risks, right? So sometimes process isolation, sometimes by just understanding the limits of your network and trying to operate depending on how your needs are, either change the operational limits or operate within those limits. Okay. The next is, now let's look at bottom-up methodology. So you look at the same stack, but see how I've kind of skewed it a little bit. I've tapered it a little bit. Basically, in our particular case, especially, what I want to do is kind of look at it from the GC perspective, right? So in my particular case, when I'm employing bottom-up methodology, my stack would look something like that. So the lens is kind of like towards the JVM and the JRE, because that's where the garbage collector resides. And that from that perspective, we're looking up to the benchmark and down to the operating system and everything else too, to be able to visualize the performance impact, so basically, this is different than the top-down methodology, because we are now able to look at lower level issues that may not be directly visible or identified from your application and application subsystems, right? So what we're looking at now is, say, from the GC perspective. So we're looking from the GC and looking at how my, say, pet clinic application behaves, or if I change, if I move from, say, Mac OS and x86-64 architecture to, say, a Windows and x86-64 architecture, then how does that change? So remember, we're looking at from a different perspective, and let's call it the low level, because in effect, everything below the application stack is a platform. So anywhere you're looking at the platform, it's called a low level analysis, which is not looking at from the application perspective, but looking from the platform up. And that's why it's called a bottom up. So now let's talk about experimental design. So designing an experiment is central to performance engineering. It involves like carefully controlling test environment and kind of systematically varying parameters to understand the impact on performance. So basically, this is what experimental design helps us achieve. It helps us have controlled experiments. We can evaluate our hypotheses, and then we can, systematically manipulate parameters. So for example, going from default G1 to the generational ZGC, that's a change, right? So we have a systematic understanding of what it means to baseline with G1 and then move to ZGC, right? And that's what it's called, like A/B testing. Okay. There are some independent and dependent variables. So independent variable would be your maximum heap size, in the sense that we want to keep that constant across both the garbage collectors that we are testing. But there are some dependent variables that sometimes, that may be very specific to G1 or ZGC. So that's something that we need to make sure. One of the most important thing about experimental design is it needs to be repeatable. So if my baseline or my the variation, the new experiment, right, the treatment is not producing repeatable results, that means that something is either we are not doing the experiment correctly, or we're not helping our test, the system under test, which in my case would be ZGC. So something is going off. So keep this in mind, and let's go and I'll try to show how we put this all together. So the way I did this with our design with the pet clinic is I'm combining both the top down and bottom up approaches, right? So I called it going hybrid. Okay. And basically, we want to use best of both the worlds. And I know what I want to do, and I know I already have a benchmark. So we're combining the top down, bottom up using experimental design. And then we kind of trying to gain understanding from different perspectives. Okay. I don't know if you have enough time, but I'm going to just quickly go through this. The reason we want to benchmark, and the kind of benchmarking goes hand in hand with performance engineering, is it's because it's needed for critical assessment of a feature release or analyzing the impact across system layers. So basically, if you have an upcoming feature release, you definitely are aware of like performance benchmarking. You're not going to release a feature without evaluating its performance. The other thing is the impact. So in my case, for example, evaluating ZGC, I want to make sure the impact is measured across system layers. So that's why we're going to do performance benchmarking. I'm going to skip through this slide, but basically, when you're doing performance benchmarking, think of it, what are your SLAs and what we're trying to achieve. Usually, because of my GC, and that's why I've kind of highlighted everything else in different shade. But because of my GC concerns, I'm looking at footprint, response times, and throughput, right? So something to keep in mind. And let's talk about the case study. I want to look at Spring Boot Pet Clinic with generational ZGC using JDK 23 early access. I'm just using the most latest. That's why I'm using the early access release. But in your case, it could be whatever you are. But generational ZGC is available since JDK 21. So just remember that if this is something that you want to reproduce. Quickly look at what Spring Boot does. It's basically a reference implementation using Spring Framework. It shows you different best practices with respect to building web apps with Spring. For my purpose, I'm just going to use generational ZGC. I want to kind of evaluate the weak generational hypothesis, which I talked about, where most objects die young. And then I want to make sure that the application performance and here performance is a very loaded term. So I want to make sure that latency constraints, because this is a Spring Boot app, and the transactional nature, which is like requests per second, kind of are steady, or at least similar to what we have seen with G1, which is the baseline that we have. Object churn is basically how we remember we're talking about transients and live data sets. So how we are handling the transients is what it means. Let's quickly look at why we're looking at ZGC. So we all know the parallel GC, which is the throughput GC. It has no concurrent work. It does have write barriers for generational maintenance, and it's a generational GC. And then we had G1 GC, which kind of became the default. It does concurrent work in the sense that it does concurrent marking, and then it does incremental compaction. So it's not fully stop the world for the entire generation. It does incremental stop the world, but its copying is stop the world. And now we have something that's ZGC, and ZGC kind of is moving more towards the concurrent nature and the latency sensitive domain, where it's kind of even doing the copying concurrently. And there's various improvements in ZGC, which I won't cover today, but something to go and read and understand, or I can come back and talk about it. So when we're talking about a low latency optimized garbage collector, I already talked about the generational part of it, which is the objects die young, right? And the small long-lived data sets. And then you have the maintenance barrier, which I talked about as in the generational maintenance write barriers. But in ZGC and in G1, you have this concept of tunable work units. So you have something known as regions. So both G1 and ZGC are regionalized garbage collectors. They both achieve partial compaction, which means that it's incrementally, it's not attacking the entire generation as a holistic unit. It's doing incrementally as needed, so to speak, so that you can have control over the pass times and the GC work. Both of them, both G1 and ZGC, have concurrent work and incremental marking, but the concurrent work in G1's case is only in the marking phase of it, so to speak. But in ZGC, it's even the copying, the object copying is concurrently done. In ZGC's case, there's like no pauses because it tries to minimize the pause and only restrict it to the most needed ones. And they both handle graceful degradation, and they both have maintenance barrier. Graceful degradation is like when your application is applying a bit more pressure, or the GC work itself is not able to keep up. Then there's a way to handle and either ask the application to back off or go into full garbage collection cycles and trying to maintain so as to not have out of memory errors. So that's called graceful degradation. Again, I can come back and talk about that a little bit more. But for now, just know that these are something that the low latency optimized garbage collectors are moving towards and optimizing your application for. Okay, let's go on to plotting the graphs. So I'll stop sharing, and then and I will share I'm going to share my desktop here so I can. Okay. Let's see what we see here. Okay. So that's ZGCs, but let's go look at so this is a bunch of scripts that I wrote to to show you the garbage collection logs and visualize the garbage collection logs. Let me know if you can see it, okay? Can you all see it, okay? Okay.
Yep.
So this is written in Python, and then I have G1 log right here. And what you see is I ran Pet Clinic for 120 seconds, and I ran it multiple times because I wanted to make sure that, again, repeatability is a concern, right? And when we're doing the experimental design. So what you is three sets. This is during ramp up stage, and then these two are like the repeatable 120 seconds runs. And ZGC, because I put XMX and XMS as 8 gigs. This is, sorry, G1 GC. It's looking pretty good, right? It's pretty steady. Your young G1 pauses are going up to the whatever the young gen reaching. And then your total heap size is right here, very steady at 8 gigs, like I said. And then if you look at heap occupancy after, so after collection, all of your young is collected and your heap is still at the maximum. And then let's look at pause durations. Pause durations are somewhere in the 5 milliseconds range. Once it reaches that kind of steady state, steady working state, it's less than around 5 milliseconds, a little bit like higher. One of the things I was talking about scaling, remember I was talking about why scaling is important, why you want to look at how your thread utilization is looking. And what we see here is the GC threads are pretty close to 2 to 4, and this is on my Mac system, so that's pretty good scaling of GC threads. The system activity is very low, which is what you want to see. You want your most of your transactions, especially in this Pet Clinic, it's a single system. So most of your transactions to be serviced by the GC and not having some system overhead. That's what you see. And then the last thing I want to show is the pause summary. So most of the garbage collector was able to adapt nicely, where you have the young generation, basically 90% of your garbage collection pauses were in the young generation, right? So young generation pauses, which is basically it's trying to age the objects correctly. Remember I talked about transients and being able to age them in the young generation. So it's able to do that. There's some metadata, which is okay. Again, metadata, and remarks. So there's some concurrent activities that happened, but we didn't need that. We were able to reclaim much of the stuff with the remark, and we're good. So this is all basically most of the operation of G1 GC with respect to this Pet Clinic are able to be in the young generation because we're able to age objects that are long-lived and kind of retrieve objects that are transient. So we're doing good with G1. And then let's go to ZGC. So I did 2 experiments with ZGC. One was with XMX and XMS, similar to a G1 at 8 gigs. So let's look at that. I think it's this one. Yeah. So let's go back quickly, and I want to show you. You see how it looks a little bit crazier because it's doing a lot of things concurrently. Remember, I talked about how the copying is done concurrently as well. So there's a lot of activities. I don't know if you can see it, but yeah, there you go. So there is this, so we can just remove these and look at one at a time. So this is young generation. So this is, again, the 3 things. One is kind of like initialization phase. This is the steady state in G1, and this is the 3rd steady state in G1. And what you see is that young pauses are, again, look at the duration. This is sub-milliseconds, right? 0.03 milliseconds. So your stop the world pauses are 0.55 milliseconds, and in G1 we saw 5 milliseconds. So already it's doing a good job, right? Although it's very scattered. So again, let's go to old pauses. Let's look at the old pauses. Even better, right? 0.044, and then it goes even further down. So overall, we're doing really well with pauses. Young pauses are a little bit higher than old because, again, there are a lot more transients, and seems like it's able to handle it well, and then let's go back quickly to the causes again. So most of the causes, and one of the things I didn't cover because we don't have time, about G1, we don't have these kind of phases. You see how we have a allocation rate, minor collection, which is young collection, proactive, major collection, which is old collection, high usage, metadata, and then warm up. So ZGC does this kind of phased, like have different triggers for garbage collection, even if it's young or old. It does different phases of collection. So warm up is in like the GC needs to warm up, which is what the initial phase that we saw. Then you had the allocation rates because the allocation rates were getting higher, so that it has a threshold for that. Proactive is like, oh, I have not been doing collect. Remember, we only saw metadata collections in old generation for G1. And so here, because there's no activity, it says, okay, let's make sure we can, give memory back. So it does a proactive collection and a high usage collection. So young generation is utilized. That's why it's minor. And once it goes past the high usage, then it goes and collects that, and then does proactive in the old generation. So that's pretty cool. That's like one of the different things we see the latencies fall as well. So that's one of them. And then I also did one more run with with just setting the XMX. So I'm just saying that whatever you want to do with the initial size and grow your heap, I just want you to stop at this point. You see, it looks a little bit better, right? We see a bunch of relocate, start, and ends and stuff like that. But even then, it doesn't go past 0.8, right? Again, we're talking about milliseconds. So it's 0.8 milliseconds. That's the latency promise that ZGC has, and it maintains that. And let's look at the GC cause very quickly. So you have allocation rate, again, because remember this pet clinic application is doing lots of transients. So of course that's going to be, 50% of that is in the young allocation. Major, again, warm up. It's warming up during the warm up side, and then proactive, high usage, and metadata. So it's able to control. So remember the high usage is smaller now because it's able to control, because I gave it the freedom to grow its heap as it wants. So it's able to control the high usage. And so that's the different things, just because we don't have time. So this is what I wanted to show very quickly. I'll send out the link for the tools and everything. And let's go back to the presentation very quickly. Okay. Sorry, we're almost out of time, I think. Yeah, let's look at that. All right. And where are we? Okay. So wanted to show the results here. As we saw, G1 GC had like lower latencies overall. It's geared towards throughput, so we have requests per second higher. It's at 17K both the time. So this is multiple runs. Remember, after the initial initialization and setup kind of stuff, these are the next two runs. They're pretty steady, pretty repeatable scores. That's the repeatability and experimental design that I was said. And this is the baseline. And then the first one that I showed you were with XMX and XMS at 8 gigs with ZGC. You see the request per second is a little bit lower, so that's the throughput drop that you see, but latencies are much better. Overall, the application latencies are much better. We could probably even tune the system to go even higher so that it can service more because it's able to handle the transients better. If we increase our pressure, like the application pressure, ZGC will be able to service more because it's keeping the latencies lower. So, which I didn't do right now because remember, experimental design, you want to control your variables that you're changing. So right now, I want to keep everything same except for the garbage collector, right? But then I did do another thing was like no XMS and then just XMS. And what I saw is the requests per second were higher, but we had a little bit of, as we saw, because the garbage collector is able to change its heap size. We got a little bit expensive application latency. Again, these are all tunables, right? And I was talking about the dependent and independent variables, and that's where we have to go and redo the experimental design, right? So let's talk about key takeaways. So we need a structured methodology to make us efficient, right? Benchmarking plays a key role in performance engineering, and JVM tuning impact should be measured against your system or application SLAs. These are the three things I want you to take away from today's presentation. And thank you all for attending.
Thank you very much. We have 10 minutes for your questions. First question. Monica, personally, I am very interested to know that does Oracle is working on new GC's algorithm right now, or the ZGC is the last one?
So ZGC is, so the way you can see the trend of the way applications are working, and I was talking about the shared domain spaces and working effectively and trying to reduce footprint and trying to reduce the CPU. So the algorithmic changes in the garbage collectors, as in like a new garbage collector, is not that important for the future. What is important is how adaptive these garbage collectors go. So we started with parallel GC. We tried doing the adaptive heap sizing algorithm in parallel GC, and we didn't go much. So the people started tuning. They started tuning survivor spaces. They started tuning young generation. They started tuning promotional thresholds and all those things. And they did a lot of tuning, manual tuning, right? So then we moved to G1. There was still, initially, there was a lot of manual tuning, but now G1 is, as you saw, very adaptive. All I did was set the heap sizes, right? And it became very predictable and very adaptive. And now ZGC is going into the domain of, as you saw, the different thresholds like warm up and high allocation rates and proactive GC. So it's becoming adaptive and gearing itself to look at to change with your application. The next thing for ZGC is the automatic heap sizing. So now when you're working in containers and in cloud and you're working with within the same domain, but with a heterogeneous, like you say, native space, and you're working with JNIs or whatever, right? So you want to make sure direct memory accesses or anything. You want to make sure that your footprint is not that big. So that's where the development is going. So it's optimizing and making your garbage collectors more adaptable rather than going into another domain space, because the trend is we're moving from throughput oriented stuff, garbage collectors, to more latency sensitive. So we can have control over GC pauses and GC copy, because copying is the most expensive operation and most disruptive operation. So if you look at the stack, remember I was talking about the hardware, you have the hardware caches, right? As you copy, guess what? You're moving in, so you're bringing in the cache line in the hardware, and then you're updating the cache line, and so you're disrupting everything. So copying is the most expensive from hardware perspective. And that's why if you look at all the optimizations we have in the memory copy, memory set space, right? Because that's where most improvements from hardware all the way to application. Like we have intrinsics, array copy, right? In Java, we have intrinsics. So things like that is where the garbage collection domain is going to be improving itself.
Thank you. Another challenging question. Which do you personally prefer, Java on Linux or Java on Windows from performance perspective?
I've been working in the Linux, so I work for Microsoft, and so I've been
Yeah.
working in the Linux space pretty much most of my work life. I joined Microsoft 5 years ago, and before that, I was working on Linux on ARM, Linux on PowerPC, Linux on Intel, Linux on AMD, Linux Solaris also on Spark. So I've been working in these domain for a long time, so I'm very comfortable with Linux personally, and Mac and Windows also. I did the Windows port. I and my team wrote the Windows port on ARM 64. So it's not that I'm not aware of the Windows space, and my desktop is Windows that I'm presenting from a Windows desktop right now. So, but personally, I'm just very comfortable. If you wake up from me, from my sleep, I can just go type commands on Linux very easily. For Windows, I'll have to take some time, get my tea or coffee before I can do something on Windows.
Thank you. Majid?
Hello, and thank you, Monica, for invaluable presentation and contribution. I truly appreciate. My question is more conceptual. When should we consider performance when developing an application? Thank you.
Yes. So I talk about this in the book and throughout various presentations that I've given. I think performance engineering, or at least the idea of having performance engineering, it should be enabled right when you're starting from the concept. When you go through a system development or software development life cycle, you still have to look at your users' needs, right? The functional needs of your application and how you're going to meet the functional needs. But there is the whole non-functional side. So you could deliver your exactly all the functional needs, right? Go check, go do this transaction with the database, make sure that you're updating all the software caches, make sure you're doing all this. And so these are your functional requirements, right? But what if that transaction that you did is not coming back to a user satisfaction level, right? That's what I was talking about, the user experience. So that is your performance needs. So those are non-functional, but they should go hand in hand as soon as you're capturing the requirements. So in your software development lifecycle, you do go through the requirements phase, right? You have to capture what your user experience and SLAs and SLOs are. And so they go hand in hand. So you start, and I have a graph in my book, and I can send it to you, but like usually they'll just walk hand in hand and they go separate ways in development. But then as you're doing performance benchmarking, you will start integrating. So when you do your unit test, for example, you also want to make sure that, hey, what I need to do performance evaluation of during that unit test phase and integration phase. All these things you want to make sure that you're able to benchmark as well, performance benchmark as well.
Thank you.
Ashkan?
Yes, I have a question about the identifying phase. You talked about the passive things, like you said that you use network taps, but I didn't quite understand what you mean by that.
So, have you used any application monitoring setups?
Yes, of course, I've used Zabbix.
Okay. So, how does that? could you give me an explanation? I want to try to explain in the stack that you have worked in. So can you tell me how does it do monitoring?
Oh yes, we actually used to see all the anomalies of the application, all the unexpected things that happens, like for example, a service goes down or something is not accessible. I used it in this way, but I didn't quite catch it, the passive part. It seems to be sometimes active. I mean, when you send a request to a service, you could see that it's not actually a response. I don't know, is it active or is it passive?
So in the passive space, it's basically you can think of it as like Snoop. Do you know about snooping?
Sniffing.
Okay. So as your data is flowing through a network, right?
Mhm.
You basically are trying to basically trying to copy certain things, and you can analyze it on the side without affecting. So your data is flowing through the network and you're just basically getting a copy of it, and then you're analyzing from without affecting the stability of your live network, so they're used to monitor kind of traffic for performance analysis and security and troubleshooting, making sure all the packets are arriving or are going to be delivered in a steady format, no dropped packets or stuff like that. So you basically gain visibility into your traffic. So it could be your
Basically,
HTTP.
we're talking about the network connections and all the things that happens on the network. I mean, it's not just about being a service being available. Yes, it means that the number of packages that is dropped in the network. This is what you mean?
Yes, exactly.
Ah,
So it's basically because most of us, when you're looking at databases, we're working with HTTP and queries, and that's what the whole the domain that we're working in is all about, requests and servicing requests, right? So those are, and you're always connected. We are always distributed. We're always connected. So sometimes, I know I didn't touch that because we're just concentrating on garbage collector today, but sometimes, you want to be able to make sure the type of traffic, and you want to optimize your resource allocation. So you're working, say, in async manner or whatever, and you have this pool of threads, and you don't want to have too much threads just spinning and not being able to get work. Or if you have that happening, then why is it happening? So those kind of network taps are really important. There's also like security. If you have potential malicious traffic that could have impact on performance or just security of the network, because you're working in this kind of domain, as databases need to be aware of these kind of stuff, and latency also. Again, why are the thread pools not utilized? Those kind of important things, and then bandwidth. So these kind of performance, you want to performance monitor those things in that kind of passive domain space. So
I see. Thank you very much.
welcome.
Arman.
Hello, Monica. This is Arman. Thank you for your nice presentation. I appreciate. As you mentioned, lock is a key parameter in optimization. In case of multi-threading environment, the resources are shared between threads, and lock is a potential problem. And when our program faces a lock, it will become slow and performance will be reduced. Is there any optimized approach, or is there any advice to avoid or minimize the locking risk? Thank you.
So, I mean, there's a lot of generic things, and I can only talk to generic things without knowing about the application and the domain that you're trying to optimize. Locks affect concurrency, but in different ways. You know, concurrency affects parallelism, right? But concurrency also affects queuing. So basically, you can think of if I had to do a scale, right? Scalability and parallelism would be the width, right? You know, you're expanding in this domain, like scale out. But queue is basically how your top down works, right? So it's kind of like top down effort, although they're both scaling, but one is scaling out on the x-axis and one is scaling out on the y-axis. So depending on where you're doing, what axis you're working with, sometimes lock-free algorithms may be better. For example, if you have message passing, right? Or like which is like the y-axis, right? You basically, there's a queue of some sorts or whatever. So, you know, going with lock-free algorithms will be better. Like atomic long is a library that you can look at. So basically going with atomics in that domain would be better. Sometimes when you're looking at scaling out, then, and which is called, which I was talking about, you know, concurrency at multi-threaded level, which is parallelism, then concurrent hash maps is something that you can look at. So there's different domains that you're trying to match, and you would need to define your problem space to use. And this is just within the, I'm just talking about the JDK. There are various other, you know, like hardware vendors will recommend certain other algorithms. So if you look at your application stack, you would need to know where your scalability bottleneck is, and then you can go and look at different tools available at that. I'm just restricting to the JDK domain right now.
Thank you very much.
Ardalan.
Hello, dear Monica.
Hello.
Thanks for your wonderful presentation. I've enjoyed it a lot. As a Java champion, I have a logical question from you. Monica, why in the recent Java versions and Java releases and in the futures roadmap that published, all the focuses are around improvement in behavior and features of the garbage collection. And we don't see the API improvements, library changes, and features like we've seen from Java 8 to 11 or 11 to 17 in programming features that programming uses a lot. And all the focuses are around the improvement and functionalities and this kind of around of the garbage collection. Is it really differ from for improvement for the garbage collection, and it's this important in Java area, you think?
So we do have, well, depending on what version you're on right now, like from Java 11 to 17, we had the switch expressions, the seal classes, the records. These are all kind of like functionality and kind of like kind of type system and the language level advancements. We also have Project Valhalla. It's been going on for a long time, but there's bits and pieces of that that's coming in to the type system improvements, kind of moving from, or kind of understanding the concept of immutability. But to answer the question of, you know, there's also other projects like foreign function interface, which is kind of doing the memory management and memory allocation space, kind of moving away from JNI, to foreign function, becoming a part of a holistic understanding of from the JVM space. There is also, like I said, Project Loom and everything. So these are also like things that are happening. I do talk about those things in detail in the book, so I'm going to skip over those. But going back to your garbage collection question, the crux of the matter is, again, remember I showed the stack. It goes directly to your hardware. What gets executed, that's how the allocation happened and how we bring in data, and then how garbage collection interferes with it. Because anytime you have a garbage collection, it's asking at the hardware level, it's saying that the mutator, especially if you have a stop the world or some kind of stop the world component, you're going into, you have a context switch to garbage collection threads, right? Or you're taking in a concurrency domain, you're taking away resources that may or may not be utilized right now when you're going into the concurrent threads. So trying to handle a garbage collection and most of the things that are not your application threads, their job is to get out of the way. So they do whatever they need to do. They need to operate in the space that you have provided them, and then they get out of the way. And you don't want your application to deal with that, right? I was talking about graceful degradation, which means sometimes, ZGC will tell your application, hey, I'm in the process of moving this object. So either you wait or you help out. So now the application is not doing application work that it's supposed to do, but it's helping the garbage collector. So how do we keep all the GC related activities to the minimum is where the performance domain is getting towards. And it is because of the sophistication in G1 and ZGC, we're able to do that. How do we handle graceful degradation better? And that's where those proactive GC and ZGC, or the high allocation rate GC. So the different conditions now to make sure that we don't get to a place where we have to gracefully degrade, right? So those kind of things we're trying to improve, and that's why you see or you hear about that, because performance domain, again, is trying to give all CPU time, everything back, or all memory or optimized memory allocations or movements or copy of data, such that the application can do its work, right? So feature development, and to support those feature development is something that's important. So Project Valhalla, for example, will also be very efficient in the way it handles memory. So it'll use processor registers more efficiently, and being able to not replicate, have copies and flatten structure. Project Loom will also talk about footprint and optimization and kind of getting out of the way of the application. All these things, if you think about from a performance domain perspective, these are just trying to avoid your application stalling or your application doing stuff that is not application specific. So that's why GC is kind of like in the middle of all that.
Thank you very much. I got my answer. Thank you.
I think the last question, if you have an advice for junior developers, Monica, what skills are needed to become a professional performance engineer?
That's a good question. Actually, all the questions that you've asked today, it's really fantastic questions. So I appreciate you all bringing those questions to me. I think to be able to be a good performance engineer, I'll just have to talk about something known as sympathy, right? When you write a piece of software, right, it's not just what it does in isolation, but it's how it performs when sent out in the world, right? and how it is going to be an integral part of the system that it's contributing towards. So if you can always think about the how, the what, and the why of the software that you're developing, you're already taken first step in understanding or empathizing, sympathizing with your work. And once you get that, you have to just extend it to the system. So a piece of software on a system, and then you look at the execution, and that's where you will be thinking about performance already, because it's not just isolation and integration, but it's also the deployment. When it gets deployed, what are we looking at? So I think just enhancing your empathy towards the deployment scenarios, I think would be a good first step for a software engineer that's performance minded or wants to become understanding of the performance domain.
Thank you very much.
Thank you.
It was a really great presentation, Monica. Thank you very much for coming, and bye.
Thank you all. Thank you for coming, and thank you for sharing this time with me. I appreciate it. I'll try to come back and talk about garbage collectors or anything else. Vote for a topic and send it my way, and I'll talk about it.
I will connect you after the session. Thank you very much.
Yes, thanks. Bye-bye.
Thank you. Bye-bye.